Okay, so here's where we were last time. We were talking about conservation of energy. I mean, I like to bring up this topic because it's a great example of why we should care about this idea of path independence. Let me make the counter argument. The counter argument, just a reminder: who needs path independence? It only applies in situations where the vector field is already known to have an anti-gradient. We can use the fundamental theorem of line integrals. Why don't we just do that? Right? It's a pretty tempting line of reasoning. So what's the response? The response is, well, if your only goal is to one at a time compute things, right? But of course, that's not our only goal. So, way I like to see it anyway, the idea of path independence is really the necessary point of view that allows you to create this concept of potential energy. If you're going to define potential energy, let's say at this point compared to that point, you need there to be a well-defined amount of work that it takes to get from there to there. In other words, you need for the work along that curve to equal to the work along that curve. In other words, you need this idea of path independence. Right? So path independence is a key concept in this very, very important idea in physics of potential energy, which of course is very, very important to this idea of conservation of energy, which of course is very, very powerful computational tool in physics, and it's a really big deal, and we can't afford to not have it. Right, so I said all the details last time. What I didn't have a chance to talk about last time was sort of a summary of terminologies. Really reminded, we've already made this observation that gradients, vector fields that are gradients of some function, vector fields for which the curl is equal to 0, vector fields that are path independent. These are all the same vector fields. Again, reminder, we're assuming everything in sight is as regular as we need it to be, so let's not worry about discontinuities and singularities and other things like that do make things much more complicated. We're not going to worry about that here. So these are all referring to the same vector fields. There are different words that we use to describe these different properties that all these same vector fields have. And they're all pretty sensible, really. These vector fields that are gradients of something, big surprise, we call them gradient fields. Highly sensible, right? Well, of course we do. That's what they are. Okay. Vector fields that are path independent. Well, we call them path independent. Oh my gosh, it could possibly be more natural, right? Highly plausible. There is a word that naturally is associated to a vector field whose curl is 0. I can't motivate this for you right now. As you know, I don't really like having to do this, but let me do it anyway. Apologies. We'll have a context for this later, but I hate having to assert geometric statements before I can give you any context for it. But I'm just going to assert, just for the purposes of motivating a term, that what curl, in some sense, computes. Right, for the moment, it's just a formula. It's a thing that we compute, right? Algebraically convenient. But in a reasonable sense of the word, it's measuring how much the vector field is representing a fluid that's sort of has a rotational component to it, a fluid flow that's going around something, as opposed to a fluid flow that's just going in a direction. So we'll give a more of a geometric justification of this later on. But anyway, with that in mind, taking my word for it, if the amount that a vector field is representing a rotation is 0, then the term irrotational. Pretty darn plausible. Think about it, right? Okay. All right. Last terminology that I want to introduce is this word called conservative. A vector field is called conservative if it's one of these fields that we're talking about. So now, where does this word conservative come from? Well, it comes from this idea of conservation of energy, right? So a conservative vector field is a vector field for which we can define a corresponding notion of potential energy. Now, how do you sort of connect that to something? Well, my personal favorite, as we've just discussed, is that you can define a notion of potential energy if the vector field is path independent. Right? I think it makes most sense to attach this word conservative to path independent. The book takes a different point of view and says we're going to define a conservative vector field to be a vector field that is a gradient of something. Doesn't really matter. These are all the same vector fields anyway. Right? So, no sweat. Anyway, in my mind, this is most naturally connected to that idea, but it does not matter. Okay, so here's a weird situation we find ourselves in. We have now, let's count them, 4 different words to describe what are, in fact, assuming appropriate regularity, the exact same vector fields. Right? So again, with assuming regularity, if you say a vector field is a gradient, that's the same as saying it's irrotational. That's the same as saying that it's path independent. That's the same as saying that it's conservative. So why are we giving you all these words? Well, it's because it's not because they refer to different vector fields. That's not the point. It's that they refer to different properties of the vector fields. Right? So the property, the feature of path independence, as a property that a vector field can have, the way you conceive of this idea of path independence is very different from the way you write down what it means to be a gradient. Right? So think of these words as being attached to the properties the vector fields hold. These vector fields satisfy a bunch of different properties. 2 seconds. So not all that unreasonable to have a bunch of different words. Yeah, go ahead.
Why is it considered irrotational?
This I commented on this before you came in, but the point here is that Curl describes the extent to which a vector field represents a fluid that has a rotational aspect to it. Yeah, you can ask me after class. Okay. So the other thing to keep in mind is all these words are in very common use, and some more so or less so in different contexts. Physicists, for example, are more likely to say the word conservative. So heads up. I mean, if you have to be aware of this word because it's liable to be the word of choice, as said by someone, some other future teacher that you might have, whatever. They might be more likely to say conservative when I might have been more likely to say gradient. And so, just, again, kind of a cultural point, but nevertheless, it's an important thing that you all have to be aware of. Okay, last thing. This function, now this is a function, not a vector field, but this is very closely connected to the idea of a gradient field. A vector field that is a gradient of something. So let's talk about what that function is. I am a big fan, as I've commented previously, of the word anti-gradient. This is the thing whose gradient is the thing that you're claiming is a gradient. So pretty darn reasonable to call it an anti-gradient. The motivation for calling this anti-gradient is identical to the motivation for the word antiderivative. Extremely plausible. So just be aware that in physics context, this is very often referred to as a potential function instead of an anti-gradient. Why would that be? Well, perfectly plausible. If you're thinking about things from a physics point of view, this is the function that describes potential energy. So, calling it a potential function, very reasonable. Again, in that context. So heads up. Our book, for example, as I recall, has a preference for this term. Potential function. So you got to be aware when you hear that word potential function. What I would like y'all to think is, they mean anti-gradient. They mean this thing. Okay. All right. Side note, ultra quick side note. This isn't a physics class, but this function is technically not quite exactly what would give you potential energy. There would actually be a minus sign. This is actually the negative of potential energy, and that's just got to do with the fact that gradients point uphill and forces point downhill. It's just a minus sign, and it's just sort of a setup construction thing. So anyway, but just be aware. Okay, so moving along now, we're going to move on to the next theorem. Let me just remind you, we've talked about so far the fundamental theorem of calculus. I gave you a point of view on the fundamental theorem of calculus that, of course, you've all seen before, I know. Right? But we have a certain point of view on it here, as that the fundamental theorem of calculus views change as accumulating over the interval, resulting in an integral on the interval of a density. All right, so these ideas of accumulation and density might be new points of view on the fundamental theorem of calculus for you, and like I say, they're going to be really important in what we're doing here. You might recall we then took those points of view, the point of view of accumulation, the point of view of density, and came up with this idea of the fundamental theorem of line integrals. Okay. So what we're going to do now is apply those same ideas in a very different context. We're going to come up with a new theorem called Green's theorem. So here's just a quick reminder again. What did we do when we were talking about the fundamental theorem of calculus? We talked about how change accumulates. Right? You can see it right here. Change accumulates. Okay. And then once we had it down to a theorem, our integrand, we were thinking again of this as an accumulation of change, and the integrand ended up being, in fact, change per unit size, and so we interpreted our integrand, f prime, as you recall, as being a density. Definitely a new point of view you haven't seen before. Okay. All right, so here's what we're going to do. We're going to come up with this new thing called Green's theorem. We're going to do it by simply taking these strategies, you might call it. We're going to try to think of something that accumulates in our new context that I'll reveal momentarily. Try to think of something that has the feature of accumulation, and then we're going to try to write it as a resulting integral, if we can, from that accumulation, and then we're going to try to interpret a corresponding notion of density. Okay, so here's our context. By the way, let me go over to our diagram here. Recall these diagrams. Quick reminder: these diagrams, I'm not trying to be rigorous with these. I'm not proving anything with these diagrams. This is just for kind of bookkeeping purposes, to give you a way to arrange these ideas in your mind, so that they're not sort of conceptually kind of all over the place and backwards and upside down, and so you can see and look for appropriate connections. It's just for organizational purposes. That said, FYI, another little cultural note. I did not make this up. What I did here is I softened an existing thing. There are some very sophisticated ideas, the real versions of all these theorems that we're talking about here, that I can't show you because it's way too hardcore. What this diagram is kind of a softened, non-rigorous, easy to swallow version of some extremely serious and extremely sophisticated stuff. So again, this is not a manufactured out of nowhere. This is comes from something that's very real. So we're trying to do something kind of like what we did with the fundamental theorem of line integrals. In the fundamental theorem of line integrals, don't forget we had this idea of we were looking at curves and their corresponding boundary points. And if you evaluate some function at that point, at those points, then that's equivalent to taking the gradient field and the line integral over the original curve of the gradient field is what you get when you evaluate the original function at the boundary points. That's our fundamental theorem of line integrals. All right. So here's where Green's theorem is going to come from, and this is pretty reasonably accurate. What we're going to do is we're just going to take these ideas and try to shift them over one spot in the diagram. I mean, that's really what we're going to do. So everything shifts over by one sort of notch on this diagram. Okay. All right, we got a lot of blanks to fill in, of course. Okay, so we're going to be looking instead of a curve and its boundary points. We're going to be looking at a two-dimensional region and its boundary curve. I don't know, seems like this is what we did in the other context. We looked at a thing and its boundary. So in our new context, one dimension higher, everything sort of moved over to the right. Let's look at a thing and its boundary. We're just trying stuff here. I'm not, this has worked before. We're optimistic it'll work again, so we're optimistically trying this. So here we are. We're going to look at a two-dimensional region like this. There's a two-dimensional region. Try to clean that up a little bit. Two-dimensional region, and its boundary curve. Okay, so let's see the boundary. The boundary is it's. I guess we've got some curve here that's part of the boundary, but then there's also this curve there. So that's the boundary. That's those are the points where if you're walking along and you're in D, those are the points that if you hit those points and keep going, now you're not in D anymore. Right, so the boundary. Okay, now awkward problem. Let's go back to our diagram. What are we going to do with our? Previously we took the boundary and then we plugged into this evaluation. So now here, if we're looking at our boundary curve, and if we want to plug into this evaluation area, if we want to do a line integral, notice a line integral requires that you have not just a curve, but a curve that has a well-defined direction. So, we do line integrals over oriented curves, right? If I want to compute, for example, the amount of work it takes to move along a certain curve, you got to see which way you're going. Right? If you're going the opposite direction, you don't get the same amount of work. In fact, you get exactly the negative of the other amount of work. But so for that to be well defined, we need to have a direction. So we can't just talk about the boundary curve. We have to talk about an oriented boundary curve. And what we're going to do here is make a convention. This is an arbitrary convention, just so that we can have an orientation, so that I can talk about line integrals, right? So totally arbitrary what I'm about to write down. That said, arbitrary though it is, this is the arbitrary convention that everybody else uses. So let's get on board, right? But it is nevertheless arbitrary. So don't look for the question of, well, why do we go that direction around the boundary? Just because. And if mathematicians had made different choices a long time ago, then we'd be going the other way. So totally arbitrary, but again, highly conventional. So here is the rule. Always go in such a way that the domain is to your left. I'm going to zoom in so that we can draw some better pictures here. So here we are going around. Let's take a point like here. Which way along the boundary can I go from that point and have the region on my left? Well, I appeal to your geometric intuition. If I go that way, then notice the region itself is on my left. Yeah? Everybody okay? This is the arbitrary choice. If you were to go the other direction, the region would be on your right, not your left. Yep.
What about the inner?
Yeah, we'll get to that in a second. Yep. Right. So, common mistake that a lot of students make is to oversimplify this and say, oh, well, you should always go counterclockwise. It's always counterclockwise. This is not true. This is a mistake. This is alluring because it's so much easier to remember and counterclockwise, and it's just, I don't know, it's easier to kind of see it and remember it or something. Doesn't work. Let's pick a point like this one. That's part of the boundary curve, right? Which way do you go to have the region on your left? Well, you go that way. The region is on my left, as it's supposed to be. Notice I'm not going counterclockwise, right? This gets you going clockwise around that inner little piece of boundary. Okay. So, anyway, there's that. Okay, always such that the region is on your left. And by the way, do feel free to note the special case that if you are talking about around the outside boundary or something, if you want to define such a thing, then yeah, it's counterclockwise. That is a special case. All right. Moving along. Okay, so we've got our region, we've got our boundary. What are we computing? Well, going back to the diagram again, in the previous context, we looked at boundaries and plugged into functions. Here, we're taking boundaries, which are now curves, and we're going to be evaluating some line integrals. I don't know. This seems like a reasonable thing to try. Don't have to, I suppose, but this is what we're going to try because it's going to work. Right, something nice is going to happen. So that's what we're evaluating. I do want to say a couple of words, though, about these evaluations, these line integrals, and that is how to interpret them. These line integrals, and do keep in mind we're talking about along the boundary. Here, let me go back to purple. Along the boundary. Okay, so along a boundary. Don't forget we're talking about a solid here in the first place, right? So we're not. It wouldn't make any sense. Sorry, what did I just do here? I just hit a weird button. Sorry, cancel. It would not make any sense to talk about the line integral, vector line integral over the green region itself. That's a mismatch. Right? Doesn't make any sense. So when we talk about, what are we computing on this region, we're talking about boundary line integral. That word boundary is important. Okay. So that keeping that in mind, here's what we're computing. We're going around this boundary. Let me remind you that as you are moving along a curve, right? When you write down a line integral, we have this interpretation, this alternate interpretation of what you're computing. You are computing, an integral along the curve of the extent to which the fluid is flowing along the curve, right? I mean, that's what this component is. This component right here says how much is the fluid flowing along the curve, right? In some sense. And, this is a new concept. We never really thought about that before. But we just realized this construction, this line integral construction, motivated from the idea of work, has a different interpretation in the context of fluids. So how much is the fluid flowing along that curve? All right, now, fine, the fluid is flowing somewhat along the curve, as I have it drawn here. But notice what the curve is doing. This is not a straight line. This curve makes an entire 360-degree turn. It has to. It's a boundary, right? Boundaries start and then go, and then it's got to kind of come back to where it was. So the curve is making you might say, a complete circle. Right? The curve itself is making it's not exactly a circle, but the direction that it's going makes a complete circle. If you are measuring the extent to which the fluid is flowing along with the curve, as the curve makes this complete circle, in a way you're measuring to what extent the fluid is going around in a circle. Kinda. Sorta. In a way, right? So with that in mind, that's the term that we use to describe this. Again, very importantly, this expression. Oh, you know what I should do? Let me, keeping in mind that we're going around the boundary, this expression, this line integral, because it's around a boundary, it represents the extent to which a fluid is kind of going around in a circle, and thus the term circulation. So this is the term that we're going to use. Now, just for emphasis purposes, very often I will say boundary circulation. That's just for emphasis. The word circulation always means circulation around a closed curve, which of course is a boundary. So boundary circulation is really what you should think of. It's a lot of syllables. Very often we'll abbreviate and just call it circulation. Yeah?
So if F is like a gradient, then why would we need to compute it? Because
well, we're not worried right now. We're just exploring. So we're not worried about why we're computing it. And that special case of if the vector field is a gradient, something very interesting does happen. It's an anomalous, it's a weird little case. And we will give some consideration to that. But right now, don't worry about it. Right now, we're just exploring. We're just kind of optimistically looking at this diagram and saying, hey, pretty interesting things happened when I considered let's compute like this, and hey, oh my gosh, look at this, we get a theorem. Right? And all we're doing right now is asking, what would that look like over here? And if I want these to be equal, what does this have to be? And thus to give me an analogous theorem. So we're just kind of trying to piece things together at the moment. Yep. Okay. All right. So boundary circulation is our object. All right. Now, the next thing we have to consider is, does this quantity accumulate? Now let's go back to our argument. Here's the argument we made about the fundamental theorem of calculus. Remember, this is what we're trying to rip off. Right? We're basically plagiarizing our own work here. Right? Hey, this worked really nicely in that other context. Let's change some details and keep the underlying idea. Let's see if we can come up with a new result. Right? So, well, if we're going to rip off all these ideas, in this other context, the big idea is that the quantity we were considering accumulated over our domain, which was an interval at that time. So we've got to ask this question, is that our new quantity, does it accumulate? Here we are. I'm going to start with a simple case. We'll get to a more complicated case in a moment. But we're going to consider a simple case where we have I'll do it like this. Okay, so here's my first region. Here's my second region. Right, and I'd like to ask the question, if I think about my quantity in question, the object that I'm considering on the green region, D1, right? Keep in mind what that is. What we're interested in computing on D1 is boundary circulation. So we're interested in looking at this quantity on D1. It's boundary circulation. Is it true that if I look at the boundary circulation on D1, and then if I look at the boundary circulation on D2, and if I add those up, right, will I get the boundary circulation on the union? Kind of like mass would, right? I mean, let's forget about boundary circulation. Let's just think of mass. If I were interested in the quantity of mass, the mass in the green region plus the mass in the blue region, if I were to add those up, I would in fact get the mass in the union. Mass accumulates. Mass has this feature of it adds up kind of sensibly the way you feel like it, of course, obviously should. I just want to ask if boundary circulation does that same thing. Okay. All right. And there's a temptation to say no. There's a temptation to say, well, obviously not. Around the union, you're doing like this, and there's no. We don't even go into this. That little piece, the knife cut between D1 and D2, we don't go in there at all. Whereas if I'm looking at the boundary circulation around D1, I am. Right, so it kind of feels like when you cut that edge that, you're making new boundary, and so you're making new line integral, and it just seems like it shouldn't work. Okay, but let's be really careful about this before we reject it too quickly. Let's write down what these boundary circulations are. We'll start with the green region. On that green region, we have as our boundary circulation. By the way, just to have some notation to write down, notice these three pieces of curve. I'm calling that piece of curve C1. I'm calling this piece of curve C2. I'm calling this piece of curve C3. That's just so that I can write write things down. Note the orientation. C1 is going that way, C2 is going that way, C3 is going that way. Just so that I can have labels on them, I've got to give them orientation. So those are my choices, conventions. Doesn't matter. Okay, all right. That said, the line integral, the boundary circulation around D1 is integral on C1 plus integral on C3. Everybody see that? Questions? Okay. Okay, now let's look around D2. Let's see here. So looking at D2, I claim this is what we get around the boundary of D2. Let's draw the picture. The boundary of D2. Well, the boundary of D2 is like that. Integral on C2, right? Plus, and now here's where the detail matters. Plus that. Integral on C3. Oh, wait a minute. In order to go around the boundary of D2, boundaries, keep in mind, you go around, so let's say counterclockwise, or, such the things on our left, right? Well, that means that direction on that curve C3. But what I labeled as C3 as a curve, just again so that I can have something I can write down and algebraically work with, is pointing up. As part of the boundary of D2, I need to go down. So what I get as part of the boundary of D2 is the exact negative of what I would have gotten if I had been going up on C3. And so I get, I have my phone. Perfect timing. What I get at that, for that piece is the negative of the integral on C3. Everybody see what's going on there? Okay. And again, vector line integrals are oriented. I mean, these are not. We're not computing something scalar in nature, like we're computing the mass on that little piece of curve or something. We're computing a vector line integral. The direction matters. If you go the wrong direction, if you go the opposite direction, you get the negative of value. So, keeping in mind the directions, we get this minus sign right here. Okay. Everybody happy? Okay. All right, so it's all over with the shouting. Now you can almost kind of see it coming. This line integral on that edge C3, you can see it appears twice, but it appears with opposite signs. Okay, I'm sorry, my pen didn't work there. It appears with opposite signs, and so when we add those up, they're going to cancel. Right? And just to finish in the rest of the details, going around the boundary of the whole thing, I get, of course, C1 plus C2. And do they add as they are supposed to? Why, yes, they do. If I add, as previously discussed, because of these minus signs, these two cancel. And these add up to that, like so. Everybody happy? So this is the weird thing. This is pretty surprising. Boundary circulation has this property of accumulation, kind of like mass does. It's like it's a thing. It's like it's a stuff. It's like we're counting ants or something, right? If there was a bunch of ants crawling around in here, the total number of ants on that piece plus the total number of ants on that piece would give us the total number of ants on the whole thing. Boundary circulation adds in the same way. Okay. All right. Now, complaint you might make, yeah, sure, that works just fine and dandy if you're only adding two separate pieces. But what if you have many more pieces like this? seeming nightmare of a situation here. So surely this is going to be much worse. And the thing is, it's not. So let's look, for example, I zoomed in too much. Let's look at how these circulations react with each other. So let's look at around the boundary of this piece. There it is. That's going around the boundary of that piece. Now let's draw a picture. What would it mean to go around the boundary of this piece? Okie dokie. Well, let's go around the boundary, always moving with the region on my left. And look what's happened. This edge here appears twice with opposite orientations. So I will be computing line integral along that edge once going up, once going down. So line integral along that edge is going to appear exactly twice in this summation. When I'm looking at these pieces over here, that edge doesn't show up at all. For this edge over here, it doesn't show up at all. That edge appears exactly twice with opposite orientations, and therefore they cancel in the summation. So altogether, then, let's just write down stuff that cancels. The line integral that you get along that edge as part of this and part of that, those cancel. The line integral that you get along that edge, well, cancel because of its two different directions thought of as part of the boundary of those two different pieces. All these interior pieces, they all cancel. Every single one of these interior pieces, all these little bitty pieces over there. They all cancel. I missed that one. What does not cancel are the pieces that are not part of the boundary of two separate pieces. So, for example, this right here, that piece right there, that's part of the boundary of that, and nothing else. So that doesn't cancel. This piece right here is part of the boundary of that and nothing else. This piece here is part of the boundary of that and nothing else. Right? So when you take all of these little pieces, we've got this great big huge region. When you dice it up into all these itty bitty little pieces and look at all the little boundary circulations going counterclockwise around every single last one of them, vast majority of those terms cancel, and the only ones that remain are those that go around the boundary. In other words, all that remains is line integral around the boundary of the original region. So this accumulation feature works just fine for not just for simple cases like this one, where we wrote down all the algebra. But you can see all that same algebraic goodness is going to happen here, even in this more complicated case. Okay. So nice punchline then. And this is a wonderfully fantastic result. Here it is. Here's our boundary circulation. Right, looking at boundary circulation around the entire thing. So in total, around the entire region, that boundary circulation is what you get when you add up over the solid all of the individual little bitty boundary circulations, and all the interior pieces cancel. All right. By the way, notice that this argument is equally true no matter how you slice it. Borrow a pun. So this is true no matter how you do the slices. So if you were to take the limit as you slice finer and finer, well, you're taking the limit of a constant. You're taking the limit of something that does not change at all. And so taking a limit doesn't change the value. So said differently, you can attach that limit for free. Now let's just look again what we have here. Here's our accumulating quantity. Accumulating quantity is written as a summation, which is then rewritten as a limit of a summation. And where have we seen that before? We had here with the fundamental theorem of calculus an accumulating quantity that we wrote as a summation due to accumulation, and then we stuck on the limit for free. Everybody on board? Things are kind of proceeding along. Geometrically, it looks very different than our picture was when we were looking at the fundamental theorem of calculus. Geometrically, it's very different, but in terms of the pattern of the argument, it's really, really similar. Okay. So the next bit here, I'm going to sweep some details under the rug. Let's go back. Oh, whoops, wrong button. Let's go back here to the fundamental theorem of calculus. We ended up with we multiplied and divided by size with the obvious ulterior motive of creating an integral. Right? So this choice here to multiply and divide by size was just, with that in mind. That having been done, though, this corresponding integrand, is it something that I can compute? Well, in the case of the fundamental theorem of calculus, yeah, totally. It's f prime of x. It was easy to see that it becomes that expression, and furthermore, it's easy to recall that this is a expression that we've dealt with previously. So it's a little different in this case. When we multiply and divide by area to turn this into a double integral, we ask ourselves this new expression here, is that something that I can compute, and do I recognize it? It's not as convenient in this case. These are details. I think in the big scheme of things, for the purposes of what we're doing here in Math 212, I'm going to say it's not important. It's very important to a mathematician. Okay, but what we're trying to do here is get some intuition, some instinct for what do these things look like, how do these ideas connect to each other, and I would call how we proceed from here kind of a detail. So I'm just going to skip over it, and I'm just going to assert that yes, again, assuming appropriate regularity, not what we're interested in here, this thing on the inside, our new integrand, is something you can compute. There's the formula for it. You'll recognize this formula, of course. This is that thing that we called Green's operator with no context back in 15.1. Okay. But before we go on, we're almost done deriving our new theorem, but before we go on, I do want to remind you sort of, what this was. This thing, that thing there, that's what we ended up with as we proceeded to kind of try to copy what we did with the fundamental theorem of calculus. This was the accumulating quantity per unit size, in the sense of what kind of an integral is this? Right? So accumulating quantity per unit size is what that was, and that's why we call it a density. Right? Well, in this context, same deal. Notice we have here our accumulating quantity, circulation per unit size. Here we're talking about a two-dimensional region. Size is now area, not length. So accumulating quantity per unit size is still going to interpret this as a density. It's now, though, not change. All right, so here our accumulating quantity was change, and thus we dubbed our new expression here change density. Now our accumulating quantity is a different thing. It's no longer change. So why would we call this change density? In our new context here, what we are talking about is circulation, and so we're going to refer to this thing here as circulation density. Okay. All right, and now let's spike the football. Here's everything we did. We made the observation that circulation accumulates. Multiply and divide by area with the obvious ulterior motive of I would like for this to turn into an integral, as you can see it does here. This circulation per unit size, we compute. Well, I asserted on the previous page that we can compute, and then it becomes this becomes this expression, which you recall as Green's operator, and we have ourselves a new theorem. There it is. This is called Green's theorem. And one of the big realizations I want you all to get out of this, one of the big takeaways, is Green's theorem is really just that's what you get when you try to reproduce the fundamental theorem of calculus in a different context. Right, and keep in mind that's what we were doing here. We looked at the fundamental theorem of line integrals, fundamental theorem of calculus. We looked at this idea of looking at boundaries, seeing what this turned into. Let's try to turn this into an integral if we can, and what is the thing whose integral gives me that? And we found that it was the gradient. We just kind of tried to reproduce that big win by sliding everything over one notch in the diagram, and what we find is that this thing is Green's operator. Oh, come on, Green's operator. And when we take a boundary curve and compute circulation, if we apply Green's operator to the field, whose circulation I just computed, and do a double integral of it, I get the same thing. Same exact pattern as we had for the fundamental theorem of line integrals and for fundamental theorem of calculus. Okay. Some notational options for you, by the way. Don't forget that vector line integrals can be written in coordinate notation like that. It means the exact same thing. It's just notationally less convenient. Right? So that said, to my surprise, it continues to be the case that very often people will write Green's theorem like this. They will prefer, instead of using that notation, they'll use this coordinate notation to represent the line integral. It means the exact same thing. It doesn't matter. It's fine. I don't really care. I just kind of wonder, why would you do that? Especially in the context of Math 212. So anyway, heads up, you're going to see it like that. Outside of Math 212, you're going to see it like this sometimes as well. Perhaps even often. Okay. One other reminder. This thing here, this is the operator that I introduced long ago as being Green's operator. I like to write it as such. And I write GRN as just an abbreviation. I just don't want to put the extra letters in there. So Green of F. It's just notation. That's kind of my notation. You might not see that elsewhere very much. My specific complaint with not having that, though, is having to constantly say dq dx minus dp dy. It's just a lot of syllables, and I'd just rather say Green's operator. It's nice to have a name. When something's important, it deserves a name. And I feel like this is important. It deserves a name, so I'm calling it Green's operating. It's just my terminology, notation. And then finally, don't forget what we're talking about here. We have an accumulating quantity, right? The accumulating quantity involved here is boundary circulation. Boundary circulation is an integral of a density. Just like with the fundamental theorem of calculus, right? Our accumulating quantity of change is an integral of a density. Change density. Here, the accumulating quantity is circulation, so circulation density. Okay. All right, let's do a quick example. We've got 2 minutes. That should be all we'll need for this example. We have here a line integral to compute. We have the curve is given to us. The vector field is given to us. How do we compute this line integral? Let's enumerate our options. One thing you could do, I suppose, is you could brute force. You could parameterize this curve. Do a pullback, right? Take a deep breath, plow forward. I guess you could do that if you'd like. Now let me show you what you're going to face if you do. That's going to be a real bummer. When you parameterize the boundary of the unit disk, that's the unit circle, and don't forget that means that you have cosine t, sine t. Don't forget what that means. That means that is your x and that is your y. So when you do that pullback, your x is going in there like that. So you're going to be looking at inside of your integral e to the power of cosine t. Now that's not, something that can't be dealt with, but is this something you really want to do? Maybe not. Right? Likewise, your y here, That's going in there and there. Again, these things can be dealt with, but just that the integral is going to be, non-trivial. All right, so let's call that plan B. Hey, here's another option. This is a line integral. Maybe you can use the fundamental theorem of line integrals. Yeah? It seems like, that fundamental theorem of line integrals was pretty awesome. It was very convenient for computing line integrals in the last section. It's not going to work. You're going to have to try to find an anti-gradient. Here's your components, right? And I claim that if you play that game, if you try to go through and find that anti-gradient, you will find that you cannot find it, that you cannot win that game. There is no anti-gradient. And I'll show you why I know that in just a few seconds. So anyway, fundamental theorem of line integrals fails. Direct parameterization, to be avoided. Certainly not something we want to do. So let's consider now our alternative. Let's use Green's theorem. Here it is. Green's theorem says if you're looking for a boundary line integral, then you can instead just compute a double integral of Green's operator. Our curve here is a boundary. See it right there. It's a boundary of that disk. In fact, it's described as a boundary right there. Okay. So, therefore, I can plug into Green's theorem. Green's theorem says do a double integral of Green's operator. Green's operator is computed by taking the P and the Q and computing as it says. Look how nice. You end up with a double integral of 2. Super easy double integral. Garden variety domain, for which I know the area, and therefore easy answer. So, Green's theorem, turns out, crushes it. Everybody on board? Questions? Okay, talk to you later. Y'all have a good Monday. See you around.